Hello, and welcome to the latest e-learning event from Petro Industry News, sponsored by Analyticalana. My name is Tom Lynch, and I'm a consultant editor for Petro Industry News here at International LabMate. Before we start, I would just like to go over some housekeeping. On your display, you will be able to see a questions panel. Please type and submit any questions in this area, and we will review as many as we can at the end of the presentation in our dedicated question and answer session. Any unanswered questions which we cannot cover in this session will be answered by email after the event. If you have any questions or technical problems with viewing or hearing today's session, please use the questions box to describe your issues, and our support team will respond to technical system questions instantly. Also, please make sure your internet speed is adequate and be aware that wireless connections may disrupt your session. We will be making this e-learning event available for on-demand review, and this will be on our website in 24 hours' time. This week, world leaders, alongside tens of thousands of negotiators, government representatives, businesses and citizens, are meeting in Scotland at the United Nations Climate Change Conference of the Parties, or COP26 as it is more commonly known, with the aim of working with every nation to reach agreement on how to tackle climate change. Therefore, it is very timely that our e-learning session today is highlighting one aspect of how analytical chemistry can contribute to the world developing and using new sustainable transport fuels to help tackle the climate change emergency. Now, elemental analysis plays a key role in all aspects of the oil industry, and it has a major role in assessing the quality and suitability of alternative non-fossil fuel sources designed to reduce CO2 emissions into our atmosphere. And today, our session will cover the comprehensive elemental analysis of biofuels and their precursors by ICP OES and combustion elemental analysis. Our e-learning experts today are all from Analyticalana, and so without further ado, I will pass you over to Victoria Kirk to introduce the speakers and begin the session.
Thank you, and hello everyone. I am Victoria Kirk, an application specialist with Analyticalana, who is located in Houston, Texas of the US. Along with myself, the speakers you will hear from today are Dr. Angela Grobel, who is our tireless senior product manager located in our headquarters of Vienna, Germany, as well as Oliver Butel, the product and applications manager for the US division, who is also located in Houston, Texas. Our session today will be broken down into 5 parts, beginning with the introduction to biofuel terminology, sources, and production outlooks presented by myself. Then Angela will introduce you to our complete solution to your chlorine and sulfur analysis needs in biofuel production. Next, Oliver will showcase the capabilities of our high-resolution ICP OES for metals analysis in vegetable oils and fats. Then I will return for a brief case study from the summer of 2021 of our dedicated microelemental analyzer for animal fat refining. And lastly, Oliver will take us to our conclusion with a short overview of Analyticalana's portfolio and what our presence in the Andrezenhauser Company means for our instruments and to you. Biofuels are biologically derived alternatives to non-renewable fossil fuels. The continually growing investments and interest in biofuels is driven by concerns about dwindling supplies of fossil fuels, concerns about environmental pollution, and goals for a carbon-neutral future to address climate change. The various sources for biofuels can be placed into broad classes, addressing their ease of production from current capabilities. First-generation biofuels are fuels made from food crops, such as corn, sugarcane, or sorghum. This can present an issue for long-term investments because it will result in a competition between food production and fuel production, which will result in an overtaxing of agricultural land. The next generation of biofuels are lignocellulose-based, also known as wood biomass or agricultural waste, such as stalks and leaves left over from corn production, as an example. The sources for second-generation biofuels are often grown on agricultural lands, but are a byproduct of that food crop production. Conceptually, third-generation biofuels move even farther away from competition with food stocks, using high lipid content algae as the fuel source. This particular fuel source has had many setbacks in its scale-up and is not expected to see large-scale viability until the middle of the century. Lastly, fourth-generation fuels focus on alleviating the issues with these second and third generations, specifically by using genetic engineering. The genetic engineering would be used to create higher yield biomass with lower lignin content and to improve the ease of processing for algae. With all that said, first-generation biofuel sources are by far the most developed for production, and specifically for the production of biodiesel. Biodiesel is synthesized via transesterification of oils or fats with a low molecular weight alcohol. The product mixture of the transesterification is then separated into wastewater glycerol, or the primary goal product, fatty acid methyl ester biodiesel, which is often abbreviated to FAME biodiesel. Sources of the fatty acids and oils are primarily food oils, with rapeseed, palm, and soybean oil accounting for over 75% of biodiesel feedstock. Used cooking oil and waste animal fat for the butchery process comprise another 20%, with a mixture of less common oils making up the remainder. Annual production of FAME biodiesel is expected to return to 2019 levels by the end of 2021, with a consistent 3% production increase trend projected to return and hold steady for the next few years. Global production of biodiesel dwarfs other forms of biofuels, and biodiesel is currently sitting between 40 and 50 billion liters of production annually. The second most common form of biofuel that consumers may think of is bioethanol. Bioethanol is a straightforward product. It is biologically derived ethanol. Most grown materials can be used for bioethanol production, though at the moment the feedstock percentages are dominated by the high-energy sugar and starch crops. For biomass or starch crops, enzymatic hydrolysis is used to break these larger molecule chains into small sugars, and these sugar solutions can then be fermented and distilled to produce ethanol. The United States and Brazil account for over 80% of global bioethanol production, which is intimately connected to the regional food productions of corn and sugar cane, respectively. Similarly to biodiesel, bioethanol is expected to return to 2019 production levels by the end of 2021, but it is still far smaller in production capacity than biodiesel, with a peak of 100 million liters per year set in 2019. The last kind of biofuel I will review is syngas. Synthesis gas, often shortened to syngas, is a gas phase fuel composed primarily of carbon monoxide and hydrogen, with a small percentage of carbon dioxide always being present. Syngas is created from the gasification of solid feedstocks, such as biomass or coal, or it can be created from the steam reformation of natural gas or other volatile hydrocarbons. The mixture of carbon monoxide and hydrogen can then be used in a variety of applications, such as the conversion into liquid fuels. The Fischer-Tropsch process converts this small molecule syngas into heavier hydrocarbons, which can then be hydrocracked into diesel or jet fuel, whereas the synthesis into methanol allows the material to be converted into gasoline via the mobile process. Syngas can be used for feedstock in the production of synthetic natural gas, which can either be liquefied or compressed, depending on the usage. But the primary driver for current global syngas production is increasing demand within China for the commodity chemical production markets, where syngas is a feedstock reagent. Even with this brief survey of biofuels, a wide range of materials, products, and even phases were discussed. Like production of traditional fossil fuels, the feedstocks, intermediates, and finished products must all be qualified and certified for both safety, efficiency, and regulatory purposes. Whether you are producing raw materials, qualifying your feedstocks, checking your byproducts, or certifying your final products, knowing what you are working with is everything. I'll now hand it over to Angela to talk about why and how we analyze all these sample types.
Independent, if we are talking about feedstock materials, intermediates, or fuels as final products. The purity, that means especially the absence of undesired elements, is a crucial quality measure and important for process safety and efficiency. Besides the metal ions, non-metal impurities such as nitrogen, sulfur, and chlorine are in the focus of our investigations. Best method, therefore, allowing measurement of all three elements in a single analysis cycle is a so-called combustion-based elemental analysis. It is a robust method which is highly matrix tolerant, providing reliable results quickly at a minimum effort. And this is exactly what makes it ideal for routine analysis in QC labs. For chlorine and sulfur, we have selected interesting application examples. Both elements have to be monitored from incoming feedstock over process stages to prevent catalyst poisoning, fouling, and corrosion processes. For final products, their content has to be as low as possible to prevent any risk in further processing. And, of course, to ensure adherence of the stringent legal limits while being used as automotive fuels like the NEX BTL. Here, the sulfur is limited to 10 ppm to protect the environment by SO2 emissions. The analysis described in the following have been carried out by aid of a combustion elemental analyzer of the type MultiEA 5100 configured in the horizontal mode. The exact system setup is summarized in the table. In order to simplify the sample introduction and to realize high degree of automation and thereby throughput, a heated sampler which allows the direct injection of highly viscous liquids was used. The combustion of the samples was flame sensor controlled, generating optimum conditions for any matrix component. This guarantees fast yet quantitative digestion. After drying of the formed reaction gases, highly sensitive detection principles such as UV fluorescence for sulfur and colorimetric titration for chlorine were applied. For analysis of the different oil and fuel samples, library methods with preset parameters for combustion temperature, gas flow, and detection have been applied. All samples, independent of their digestion behavior, boiling point, or element content, have been analyzed with the same method for chlorine or sulfur determination. This is possible due to automatic process optimization by aid of flame sensor and the wide linear working range of the used detection systems. A matrix-related adaptation, as in the past, is no more necessary. But enough hardware. Let's have a closer look to the first application example. Analyzing fatty acids like vegetable oils is always a challenge due to their enormous chain length, resulting quite often in incomplete combustion and system contamination. But the here analyzed palm oil is even worse due to its inhomogeneity, high viscosity, and partly multiphasic character, requiring always special strategies for sample supply. Without a treatment, results will be widely scattering, non-repeatable, and incorrect. This can be prevented only by manual direct dosing after sample was melted in a water bath, or a little bit more comfortable automatically after sample dilution with a suited solvent like in our example here with xylene. Or what is even more comfortable, without any additional hand grip, by utilization of a heated sample supply system which melts the sample before direct injection into the analyzer. Let's have a closer look to the gained results for the two different palm oil samples. The total chlorine is quite low, as required for feedstock materials and further processing or just for final products for consumers. Thanks to the applied dilution, repeatability of the results and the correctness, which was tested independently by analysis of the CRM, is quite good for such an inhomogenized material. But in some cases, it is not enough to just know about the presence of the chlorine. For better process optimization and elimination of contamination sources, it is necessary to know exactly about the type of the chlorine compound. This slide depicts the analysis results of the separate determination of inorganically and organically bound chlorine. Before analysis, the oil sample has been extracted by hand-warmed distilled water for at least 10 minutes by aid of an ultrasonic water bath. After complete phase separation, the aqueous extract was analyzed for TiCl, the total inorganic bound chlorine, by direct injection into the titration cell. Afterwards, the remaining sample was combusted. Like in the example before, the result gained was a total organically bound chlorine. The results show that the biggest contribution comes from the inorganic sources, which can easily be removed before further processing. The remaining organically bound contributes below 2 mg per kilogram to the entire contamination. And here's an example for total sulfur according ASTM D5453 by UV fluorescence. This is a highly sensitive detection principle combining ultra-low detection limits with a wide linear operation range. This enables direct measurement of widely varying element contents with one and the same analysis method and system configuration, without the necessity of an additional dilution step, allowing faster processing. Quantitative digestion and dosing at higher temperatures plays here an important role too, especially for any sample matrix with viscosity above 10 centistokes. The analyzed samples here are characteristic biorefinery materials, representing the ultra-pure final products like the green diesel with a sulfur content of approximately 211 ppb, and highly polluted feedstock materials like the bio-crude oil with a sulfur content in a lower weight percentage range. The reproducibility of results is nearly content independent, which is a good measure for the quality of matrix separation, but also for the repeatability of the sample dosing. A crossover or memory effects between the different concentrated samples have not been obtained. The secret behind optimum digestion is a simple sensor control and adaptation of combustion and sample supply process. The scheme depicts the function of the flame sensor with a green curve. The red curve is characteristic for the widely spread parameter mode, often accompanied by incomplete combustion, soot formation, and deflagration. The blue line is a threshold for a complete combustion, which should never be exceeded to prevent these effects. While the sample boat is transferred into the furnace, the sample starts to evaporate. The formed gaseous components are combusted subsequently. The flame generated is monitored by the flame sensor. As long as it is below the pre-regulation value, the boat moves forwards. If the limit value is reached, the movement is stopped to avoid further evaporation and thereby uncontrolled and incomplete combustion. As long as the value stays, the boat waits at a safe position. Only if the value decreases, the forwards movement is restarted. Even in case of further increase of the value, the sensor prevents soot formation by just pulling the boat backwards into a colder zone. When the flame extinguishes, the movement is accelerated to save valuable time. This optimization contributes in an improved precision and repeatability of the results. For the introduced application examples, combustion elemental analysis offers many advantages. The high sensitivity and wide linear operation range allow the direct analysis of any concentration without sample pretreatment step ahead of measurement or multiple injection for enrichment. And this by using only one and the same method, simply comfortable, less labor intensive, and failure prone. Fast results with high precision for even most challenging organic materials are supported by the time and matrix optimized combustion, ensuring a complete matrix separation. Matrix adaptable dosing techniques like the temperature-controlled autosampler eliminate error sources, remarkably decrease sample processing time, effort, and costs, and thereby increasing the throughput speed and efficiency of the lab. To measure more sensitive or faster is only possible by the high-resolution ICP OES technique. And with this, I would like to hand over to the next interesting application example.
Thank you, Angela. We are now going to take a closer look at the analysis of trace metals in vegetable oils and fats using the Plasma Quant 9100 Elite high-resolution ICP OES. The samples we analyzed are a variety of different vegetable oils, including palm, rapeseed, corn, and soybean oils. And these kind of samples can be solid or liquid at room temperature, depending on their fatty acid composition. We are analyzing quite a range of different elements that can all have a negative impact on the production process as well as the product quality, including elements that could, for example, form deposits in combustion engines, contribute to toxic emissions, or have a negative impact on the refining process, for example, by catalyst poisoning. These organic samples are quite challenging to an ICP instrument and therefore require a robust plasma, and we need low detection limits to ensure a consistent high product quality. Sample preparation for this analysis is simple and straightforward. The liquid vegetable oils are simply diluted with a suitable solvent. We used xylene here in this example and a dilution factor of 5. The vegetable fats that are solid at room temperature are first melted in a water bath at about 60 degrees and then diluted the same way. These sample dilutions will be stable over a few days. Looking at the instrument parameters, we are working at standard settings for organic solvents. The addition of oxygen into the plasma is optional, but can help to eliminate soot deposits in the plasma torch, and the oxygen will also greatly reduce the spectral emissions of the organic matrix and therefore help to clean up the spectra and achieve lower detection limits. We are working with a solvent-resistant sample introduction system and a calibration range of 0.1 to 5 milligrams per kilogram, which corresponds to the typical concentration ranges of these elements in this kind of samples. Yttrium is used as an internal standard. The analysis of organic sample solutions presents certain challenges to an ICP OES system when compared to the analysis of aqueous solutions. First of all, the organic sample matrix requires a lot more plasma energy than aqueous samples, so an efficient and robust plasma system is required. Also, the carbon-rich organic matrix can lead to soot depositions in the plasma torch, which would in turn lead to signal drift, poor precision, and poor long-term stability. To eliminate these effects, the plasma quant uses the vertical V-shuttle torch design, which is very resistant towards these soot depositions, but also the addition of oxygen into the plasma can further eliminate soot formation so that the instrument can be used for a long time before cleaning is required. The carbon-rich matrix also leads to lots of optical emissions across the entire spectral range, making the spectra more complicated and increasing the risk of spectral interferences. Here, a high-resolution optical system greatly helps to have all the primary, most sensitive emission lines for the analyte elements available. And again, the addition of oxygen into the plasma can also greatly reduce to almost eliminate these carbon-based spectral emissions. Detection limits in the microgram per kilogram range are required to ensure the product quality. So the most sensitive emission lines should be used, and a highly sensitive instrument system is required. When we look at the table on the right, the method detection limits MDL are all in the low microgram per kilogram range. And when we look at the spike recovery, which is near 100% for all the elements, we can see that this analytical method provides a high precision, accuracy, and sensitivity. Here we see the spectrum of nickel in these samples, and in the spectrum on the left, you can see these very tall emission lines. These are background emissions from the organic sample matrix, and the nickel emission line that we want to analyze becomes almost invisible between all these very tall background signals. When we add oxygen to the plasma, the spectrum on the right is the result. We can see that not only have these background emissions been almost completely eliminated, but also the baseline is much lower, and the nickel emission line can now be evaluated properly. And this leads to a drastic increase in the detection performance. Depending on the element and wavelength we are looking at, the addition of oxygen into the plasma can improve the detection limits up to several hundred times. In routine analytical environments, long-term stability is of course very important. And here we see the spike recovery for spiked samples over a period of 8 hours, and you can see that during the entire time the recovery was between 90 and 110%, proving an excellent long-term stability and accuracy of the measurement results. We used the OIL 7400 autosampler from Teledyne CTAC. This autosampler is designed for the analysis of both aqueous and organic samples with its dual rinsing port. It also has a stirrer to homogenize the samples prior to the analysis, as well as a completely solvent-resistant construction. Concluding this example, we have seen that the analytical procedure is simple and straightforward. Sample preparation only requires dilution. Ashing or digestions are not required for sample preparation. The highly sensitive instrument system provides detection limits in the low microgram per kilogram range, even in these challenging organic samples. And the highly robust and stable plasma system provides excellent long-term stability and therefore reliable routine analysis. The high spectral resolution simplifies method development and virtually eliminates the need for spectral corrections, and therefore leads to trusted results and reduced efforts for data review. The Plasma Quant is accompanied by a comprehensive range of accessories that allow unattended operation at a high sample throughput in routine environments. And with this, I would like to hand over to Victoria.
Thank you. I'll now be presenting a simple case study for biofuel analysis that highlights the versatility of Analyticalana's MultiEA 5100 with a 2021 installation in the US. The client approached us with this challenge to analyze both their raw materials and finished products for sulfur, nitrogen, and chlorine on the same instrument. The raw materials were solid beef fat and a viscous corn oil, both of which contained a magnitude higher content of sulfur and nitrogen than the finished product, biodiesel, all of which are pictured. The ease of use in both sample preparation and using the instrument, as well as the ability to run unattended, were other desired features for this application. The first step in increasing the ease of use for technicians was doing away with dilutions for the corn oil. The beef fat is a solid at room temperature, and the biodiesel is a semi-volatile liquid, but the corn oil is too viscous for handling with a thin needle and syringe. Instead of diluting the oil, I found it was sufficient to just use 2 drops on the quartz boat as shown. This is both far faster to measure out than dilutions and faster to analyze because a diluent measurement is no longer required. Which brings us to the instrument. Angela introduced you to some of the features of the MultiEA 5100, but I will present the specific arrangement used in this installation of our case study. Because the EA 5100 system is a highly customizable instrument intended for the analysis of organic matrices, every installation requires some thought and collaboration with the client to choose their right solution. All EA 5100 units can be run in either vertical or horizontal mode, where vertical mode is intended for gases, LPGs, and volatile liquid samples. Meanwhile, the horizontal mode is intended for the longer combustion times required for solids and non-volatile liquids. From our case study, which requires analyzing both solid fats and semi-volatile diesel on a daily basis, we determined that the horizontal mode of operation was best. The horizontal mode also allows the system to take the advantage of the flame sensor technology, where the rate of sample combustion can be controlled by the automatic boat drive as a function of the brightness of the combustion flame. The flame sensor technology, as well as the self-check system, allow for the complete and safe combustion of every sample every time, with no required input from the user. Every combustion generates nitrogen oxide, sulfur oxide, and hydrochloric acid, which are then flowed into the modular detection units. The full range of sensitivity is available in our nitrogen chemiluminescence detector, as well as our sulfur UV fluorescence detector modules. For the chloride module, the high sensitivity cell was chosen in order to accurately measure the low levels of chloride that is present in most biofuel and fossil fuel feedstocks, as well as their end products. Let's now take a look at the results, both numerical and for the end users. In the table on the right, a selection of the results from my method development process are shown. The tables are provided by the client, and each was analyzed in triplicate to determine the average values and standard deviations. You can see that the nitrogen and chloride contents of the solid fat are significantly higher than that of the oils or biodiesel. The highest variation is seen in fat A for nitrogen, but that 12.6 ppm only comes to a less than 4% relative standard deviation. The limits of detection for the modules installed are 0.02 ppm for both nitrogen and sulfur, and as low as 0.01 ppm for the chloride module. In the lab, the end users appreciated several of the ease of use features that are a part of the EA 5100. For example, a daily factor is a QC standard that can be used to check and readjust calibration for increased day-to-day accuracy, while the high sensitivity chloride cell only requires a daily check for fill levels and an only once weekly cleaning. The end users were able to quickly begin using the instrument without the need to stress over method parameters, thanks to our preloaded method library, which allows the users to simply activate the method they wish to run. The EA5100 comes preloaded with a large number of ASTM and UOP methods that are appropriate for the installed instrument configuration. And lastly, the automation via the multi-matrix sampler and the automatic boat drive system allow the users to run up to 112 liquid samples at a time, or 35 samples in one sequence with no user input after hitting go. With a review of my short case study now done, Oliver will now bring us to the conclusion of our session.
Thank you, Victoria. And to conclude today's webinar, I would like to give you a brief overview of the Analyticalana product portfolio for the analysis of biofuels and refinery products. The portfolio includes a wide range of atomic spectroscopic instrumentation, including atomic absorption, ICP OES and ICP MS, UV-Vis spectrophotometers for molecular analysis, as well as the MultiEA and compact elemental analyzers, and complemented by environmental parameters like AOX organic halogen analysis and TOC total organic carbon analyzers. Analyticalana is part of the Andrezenhauser Group. While Analyticalana provides instrumentation for a wide range of lab analytical techniques, Andrezenhauser manufactures sensors for a wide range of different process parameters like flow, pressure, temperature, but also chemical parameters. With this combination, the Andrezenhauser Group covers the most diverse range of instrumentation for the biofuels production, and therefore is your ideal partner for all your analytical needs. Now I would like to thank you for joining us in today's webinar, and we will now open the session for questions. Thank you very much.
Thank you, Victoria, Angela, and Oliver, for that fantastic insight into the latest trends and developments by Analyticalana for the elemental analysis of biofuels and their precursors. Again, to remind the audience that a recording of today's event will be online at Petro Online in the next few hours for on-demand access, so you can review key points of interest, share it with your peers and colleagues at your leisure. Now, we have a few questions that have come in, but if any of the audience have any further questions, please type them in the Q&A box and we will get into them in the Q&A session, which we will now start. So we have a question here for the speakers, which is, how is the sample weight handled during automatic sample reduction of solids? This needs to be linked to dedicated samples in order to calculate the mass concentration.
Yes, hi, this is Victoria, and I'll handle that question. For the EA 5100 solids, that sample information for your weight that is put into the boat is entered alongside what the sample name is. Just that way you can choose if you're doing mass for your solids or mass volume, or even if you're doing mass volume for liquid or mass by liquids, you can enter the density of your sample and get that mass for your liquids as well. So you enter the sample weight, just type it into the software, and that's how it is calculated at the end for your result.
Okay, thank you, Victoria. Another question here is, what kind of nebulizer and spray chamber did you use for the oils analysis on the OES system?
I think I will hand that one over to Oliver to answer.
Yeah, thank you. Here in this example, we used a standard concentric nebulizer with a cyclonic spray chamber running at 0.4 milliliters per minute. But we do have other nebulizer spray chamber combinations available depending on the specific application. These might include nebulizers for elevated particle content in the samples that can sometimes occur depending on the type of samples, but also temperature controlled spray chambers to run the more volatile solvents.
Okay, thank you. We have a question here. I presume it means for the Elementa analyzer. How can the instrument measure gases and LPGs? I'm not sure whether that relates to biofuels, but it's a question we have to admit.
Yeah, so I'll take that one again. We have Analyticalana offers dedicated modules for atmospheric gases to be measured, as well as a module that is specific for LPGs that can handle those higher pressure, samples. And then we have a combi one for if you're in a lab that is measuring both the gases and the LPGs that are coming off. So you can measure, and all of those are associated with the EA 5100. So you can be analyzing your gases for nitrogen and sulfur content and chloride content quite easily.
Okay, thank you, Victoria. I have another question here. What is the maximum boiling point of the sample that can be introduced on the vertical EA 5100?
I can go ahead and jump in on that one. There's not really necessarily a hard high boiling point, but really diesel and biodiesel really are kind of hitting that top end of that viscosity boiling point combination for the vertical introduction. For biodiesel and diesel, we actually recommend in putting in quartz wool to the combustion furnace to make sure that there's no particulate or no droplets that are unfully combusted by the time they reach the bottom of the combustion furnace.
Okay, thank you. Just another question here about standardization. For the ICP, do you have metric match standards, or are the special standards organic standards, or do you use aqueous standards polluted and organic solvents for the mixing problems? Is that an issue here? Specialized standard solutions you need?
I'll let Oliver handle that one.
I'm sorry, can you repeat that question, please? It did not come through very clearly.
Okay, the question is just the standards you use for the ICP. Do they have to be specially matrix matched with the analysis matrix, or are there special organic solvent standards you use?
Yeah, thank you. So basically, we try to keep the calibration standards as similar as possible to the samples, which means that, first of all, we are using the same solvent to dilute the samples and the standards. Depending on the viscosity of the original samples, especially at low dilution factors, we recommend adjusting the viscosity of the calibration standards using blank oil. and the standard solutions themselves are organometallic oil-based standards.
Okay, thank you, Oliver. A question here. Can we analyze low volatile fuel directly?
I'll take that one to address it for the EA 5100, but I think Oliver might talk about it for the ICP. So for the EA 5100, yes, low volatile fuel can be analyzed directly. It's actually recommended, one of the recommended uses. You can either, and if the volatility is particularly low or particularly high, we have a cooled matrix auto sampler that can make sure that they don't evaporate off too quickly while in the syringe. Oliver, would you like to address how we handle low volatile fuels for the ICP?
Yeah, of course. For samples with high volatility, first of all, we recommend to use septum-capped sample vials. On the auto sampler, we do have an auto sampler available that has a septum piercing capability, just to prevent evaporation of the samples while they are sitting on the auto sampler waiting to be analyzed. And then for the sample introduction, we also recommend a temperature-controlled spray chamber that can be cooled down to temperatures below room temperature. And with that combination, volatile samples can be analyzed very easily.
Okay, thank you. There's a question here about maintenance. I think asking how much time is it between cleaning the torch and the plasma chamber for soot? Is this less than the conventional hydrocarbon oils as you're using biofuels?
I think Oliver can definitely answer that one.
I can do that, yes. Well, the cleaning intervals obviously depend quite a lot on the type of samples and how many samples you run every day. In most cases, cleaning once a week is sufficient, and with more difficult samples, the cleaning intervals might be a bit shorter, but typically once a week in routine analysis should be fine.
Thank you. A question here, is there an option to automatically dilute samples in the auto sampler for the EA 5100?
I can go ahead and answer that one. There is not, but the sample size being introduced can be fully adjusted. We even have different size syringes that can be added onto the auto sampler if you need those lower sample injection volume. So that is available. So if you down to, I think about 10 microliters is the smallest injection volume, up to about 500.
Okay, thank you very much, Victoria. We have now come to the end of our live session. So thank you again, Victoria, Angela, and Oliver, for your presentation and the answers to the audience question. Any questions which we did not manage to cover in the available time or which would come when people access online later will be answered by email after they come in. Thank you to our audience today for attending this e-learning session brought to you by Petro Industry News and sponsored by Analyticalana. Also, please feel free to request your certificate of attendance, which you can see will be available on your screen for download. Also, look out for the next e-learning sessions to the end of 2021 and beyond by visiting petroonline.com and click on the e-learning tab at the top of the page to see details of future events, but also to access recordings of all the past e-learning events. Until then, have a good day. From me, Victoria, Angela, and Oliver at Analyticalana, and from all the Petro Industry News team, thank you, stay safe, and until the next time, goodbye.